Okay, now we're live. How is the sound quality? It's good. Alright, gotta go over to YouTube. I gotta check how it is on there. I'm gonna mute it on my restream. There. I was gonna see how YouTube is. I don't know, maybe it's kind of loud or that's good. Maybe it's good. Okay. Man, where's... Oh, I got my water. Yes. Okay, so we're going to be doing the amplification application of transistors. Alright, I hear the Twitch stream also. And we're keeping up our bit rate. Yeah, that's great. Okay. No. Did I speak too soon? Maybe it's good. I'm gonna keep one stream running on, I guess I'll just choose YouTube. And I'm gonna mute it, but I gotta keep it running, I guess. I don't know, to ensure that I don't get any skips. Okay. That's all good. And this is where we were at. I guess I kind of understand that, so this is where we're at. Hartley oscillator. Okay. So we're going to use the common emitter amplifier to amplify a feedback signal, and continue to do this in order to generate oscillations or generate a frequency. So we're essentially going to produce a frequency generator, which we should be able to make variable by a variable capacitor. This capacitance is going to change the frequency at which it resonates, and so on. So let's go ahead and finish drawing this out. How's that? Can you see that? Yeah, that's right, and that's where our output is. Okay, down to our LC tank circuit, which is going to look like this. And then we got these split connected to ground here. And then yes, the rest of the common emitter amplifier, which is this portion of the circuit. And then I think, yeah, the capacitor in parallel here. Whoops, I made that too much. Then we have him grounded just like that. And yeah, like that. Best way to draw it, I guess. R1, RC, VCC, label it now. R2. RE. We call him Q, I guess. Okay, Q1. I wonder, can you see that fine writing like that? Man. Let's see, not really all that great. We can zoom it in though, that's for sure. Oh, that's nice. Okay. I just figured out studio mode on OBS Studio. That's nice. Okay. There, finally it's zooming in. The delay is crazy. Holy smokes. And then what, we should be able to pan it more? Nope, other way. Oh, that's so much better, isn't it? Yeah, the delay is crazy. It's still taking forever. Yeah, that's nice. Okay. Alright, Hartley oscillator. Let me mute this. Alright, there. Okay, Hartley oscillator. Let's see. We have to do a 180 degree phase shift through first transition is the transistor, and then second transition is following the capacitor, adjustable capacitor, variable capacitor. Call it B, L2 or L1, B, this B. Satisfy the Barkhausen criterion for oscillation, the AVB product must equal 1. Solving for AV gives us, or, okay, very well. Yeah, figure out therefore the frequency of oscillation labeled F oscillation equals the frequency at which XLI1 plus XLO2 plus, or equals XC3. Okay. So, yeah, we're gonna use, well, I guess they don't even have any values, but this is very good. Alright, this is what we need. So, AV, that is the voltage amplification by the transistor. And so, okay, this is what we're going to do by the LC. So we start here with this branch. Okay, and what do we label this? C3 variable. L1, L2. Yes. CE, C2. Bitrate is good. Recording, okay, tight. Alright. Grounded, what do we label him? C1. C2, C3, yes. Okay. Appears capacitive. Also the net. Yeah, sure. And then you could draw it in that form. Okay. The net capacitive reactance of the L2 C3 branch equals the inductive reactance of the L1 branch. This gives us the following mathematical relationship. Mathematical relationship XL1 equals, okay. XL2, XC3, XL2. Sure. Okay, so this is gonna be 2 pi f. Oh my gosh, why am I drawing a blank? L. 2 pi fl equals 1 over 2 pi fc minus 2 pi fl xl2 l2 l1. Yeah? 2 pi fc 2 pi fl. Wait, but it's not so easy. Wait a second. Therefore, the frequency of oscillation. Oh, because we'd be solving for f. Yes. Oh, okay. So now we solve for f, essentially. Yeah, that's what's happening. Okay. 2 pi. Wait a second. No. Yeah. No. Yeah. Okay. So we're gonna multiply by f 2 pi f squared L1 plus 2 pi f squared L2 equals 1 over 2 pi c. Okay, yes. Yeah, no. Okay, so what are we solving for? Solving for f. Okay, so yeah, f squared 2 pi L1. Okay, L1 2 pi plus L2, like this, equals 1 over 2 pi c. Okay, so divide by 2 pi, so 4 pi squared c times, okay, so equals 1 over 4 pi squared c L1 plus L2, and that's f squared. F equals, well, square root, so we can pull those out. Square root of c times, okay, 1 over 2 pi square root of c L1 plus L2. Okay. Yeah, okay, hopefully that's all good. Hopefully you caught that. And that's definitely, that's what our book has right here. Okay, let me label them to C3. Oh, C1, C2, that's C3. Okay, the feedback voltage VFB driving the base of the transistor is developed across the inductance L2. Feedback voltage. Feedback. Is that labeled? Wait. Driving the base of the transistor is developed across the inductance L2. Really? Oh, yes. Oh, for sure. Okay. Being developed across L2. Okay. The inductance L2. Similarly, the output voltage is developed across the inductance L1. As you recall from section 2.1, the ratio of feedback voltage to output voltage is the feedback fraction B. Okay. So, B equals VFB divided by VL. VF B divided by V out. Okay. And then, yeah. Okay. And we can define it by I times the reactant to pi FL2. Yeah, that's correct. Okay, yes, equals I times, I don't like to write it like that. I don't really like to write it like that either. I guess, you know, without the arrows, but it just reminds me of vector and dot product. Or if you wrote a multiplication as an x, it would remind me of the cross product. Like, I don't like to write it that way for that reason. So I'm just gonna put it in parentheses. This is what we'll do. And times x, yeah, xl2 divided by I times xl1. Yeah, that was good. 2 pi fl2 to pi fl1. And so this reduces to L2 over L1. And that's our feedback driving the base. As you recall, the ratio of feedback voltage to output voltage is the feedback fraction, B. So, feedback fraction. B. Sure. Okay. To satisfy the Barkhausen criterion for oscillation, the AVB product must equal 1. Solving for AV gives us, okay, AV, where AV is the voltage amplification, the gain. It's the gain. It's the voltage gain. With regard to the transistor's, you know, properties, which is going to depend on the bias point and, I guess not really. Wait, yes? I don't know. I'm still figuring something out regarding that, I guess. I'd have to think about it. But here was yeah, this says that the voltage gain of the common emitter amplifier must equal at least the ratio L1 over L2 in order to overcome the losses in the feedback network. Oh, yeah, we didn't write this. Let's write this. So, AV equals 1 over B. Yes, okay. Did I spell that right? I did. Criterion for oscillation. Criterion, AVB product must equal 1. AV B equals 1. That's Barkhausen criterion. Yes. Okay. AV equals 1 over B. AV equals L1 over L2. Yes. Okay. Barkhausen criterion so that we can sustain oscillations. In order to overcome the loss in the feedback network, right, common emitter amplifier must equal at least the ratio L1, L2 in order to overcome the losses in the feedback network. Therefore, yes, sustaining oscillations. Overcome the losses in the feedback network. Okay, so L1 over L2, AV. Interesting. Okay. Well, for the 2N3904 transistor, because this is what I've used in my amplification circuit previously made, is approximately like 100 to 200 gain. So within that range, this is what we can bet on. Yes. That'll give us that. So AV must equal 1 over B, where B equals, yes, L1 over L2. Okay. Is developed across that. Find relationship. Since it is desired to have b equals 1 over 20, the following relationship is true. Wait. Yeah, I already have an amplifier with a gain of, we're talking about voltage. It's literally only 5.775. I guess let's just run through it. Let's see what it would take to use that gain in order to sustain oscillations. I'm not sure what effect this will have, whether it would be a lower frequency or what, but let's do it. L1 over L2, so now we're gonna have to count, well, not for the bias operation point. Yeah, so we want AV, okay, desired. AV equals 5.5. Let's say this. Desired AV equals 5.5. Yes. Oh, that doesn't really matter though, because now we need to figure out this. So what's this gonna look like? Well, it's separated from all of that, so just the common emitter amplifier. Oh, you can see that shit. No, you can't. Okay, there. Right? There. Whoops. I'm not drawing this very good. I really messed up. Oh well. Okay. This is our common emitter amplifier. Here's our output. And it's decoupled with coupling capacitors C1 and C2, so we're not gonna consider anything outside of those capacitors as part of this this DC circuit, because we're gonna be finding the operation point for the transistor to set. Well, I guess I already have all that. Wait, I already have all that. I mean, I guess I haven't done it on the stream though, so perhaps I should I could go through that. Yeah, I gotta see something. I guess I don't really care. Fuck it. No, let's go ahead and roll with that. I have that already. So actually, all I did need was this. So 5.5. Let's say 5.5 equals L1 over L2. So let's see what common values I have. And then what we have to consider, they have a resistance. I was operating at, I have it wrote down where? Right here. I wrote down here, the DC doesn't get past that, so it would matter. And I was applying 165 millivolts. Can't believe I didn't write it down, but the maximum, or well, the output, the signal output. So 165 times, yeah, 5.775. Okay, right? Yeah. So it's approaching one volt, 0.953. We'll round it. What I do in my pen? What the? Oh, duh. Shit. All right. So V out equals 0.953 volts. Yes. So. Oh. I mean, I have it right here. So 0.95253. Voltage peak to peak. Oh, PP. It just is what it is. Okay. You know, or 953 millivolts. Yes. So peak to peak. This is our output. Right, and so I want to look at, yeah, because the smaller they get, the smaller their resistance. 1.5, okay, right here, 2.7. Okay, the highest we have is 23.3 ohms at 10 millihenry. That's high. Let's not do that. Let's, what do I got? I got 2.2953, man. Wait, they have an ohm rating, but, yeah, just stay under that. 1 millihenry, 600, 470. Let's try this. 470 microhenry divided by, what that be, L1. Yeah, because that's developed across there. And then that's developed across there, and we need that to be approximately 1.6. And that's developed across, yeah, there. Wait, so is this going to come from a mutual inductance? Is that what's happening here? Is that coming from a mutual inductance? Impedance to AC signal. This effectively isolates a transistor collector from AC ground. The DC resistance of the RFC is negligible. However, the resistor R1, R2, and RE provide the circuit with the proper DC bias. So that's oscillating frequency is 4 megahertz. If C3 is adjusted, 300 picofarads, and the desired feedback fraction is. Yeah, because F oscillation. Alright, well, what do we want our frequency to be then? That's the question. Let's do... let's shoot for our frequency of... 2 kilohertz. Yeah, that's within the range of my oscilloscope. 2 kilohertz. I like it. It's a good number. F equals 2 kilohertz equals 1 over 2 pi square root of C L1 plus L2. Oh, I didn't need that last one. Whatever. Okay. 2 kilohertz, 2 pi times 4 kilohertz, 1 over square root. Okay, square equals 1 over C L1 plus L2. That's going to determine a value of C. Did they suggest something? They suggest solving for L2. Yeah, wait. If C3 is adjusted 300 picofarads and the desired feedback fraction is Word, okay. Mm-hmm. 1/20, 1/0.188. Heck no. Okay, the minimum voltage gain AV required of the common emitter amplifier to sustain oscillations. Let me look at something. Dang, my last circuit kind of looked like dog shit. But we're gonna keep moving forward. Man, I need some more water. Okay. So let's say we got a let's say we got L1 over L2. Yeah, so 5.5 L2 L1 equals 5.5 L2. Okay. .5 times L2, we could say L2 equals, but first we have to, yeah, so we could define that. Oh, okay, so we could say 1 over L1 plus 5, or L2 plus 6.5 L2. 1 plus 5.5, yeah, so 6.5 L2. C. So pi squared 16 kilohertz. Pi squared 16 kilohertz. 6.5 times C. 6.5? No, because that's what that would equal. I could have wrote it. Okay, there. I don't know, variable capacitance. Man, I do have variable capacitors, but like, I don't have the packaging, so I don't know. I don't have a single idea how much they're worth, what their values are. I could just put an electrolytic capacitor. Here's a variable, but I have no idea. Ooh, why is he all dirty? It's kind of dirty. Does my oscilloscope have a capacitance measurement? Man, let's try it. Let's see. I want to measure it with this though. Let's measure with the other probes. Here they are. No, they're not. Oh yeah, they're in the case, which is right here. you can't even see that. Oh, see, now I gotta zoom out. That's fine. Okay. Oh shit. Man, the Viz Lumen is in the way. Oh yeah, okay. Properties. Oh, not really what I'm looking for. It's max tilted. I guess I can just throw it out here. Jeez. That's fine for now. That's all I need. Okay, too much tilt now. Okay. There, that's okay, that's all I needed. Let's see if we got a capacitance. Signal settings, multimeter. Probably a multimeter. Oh my gosh, I do. No? Because what, it's really turned to 0? That's, ah, man, where's, that's fine, I don't need that. Let's, I just don't want to put these down, but there. And probably that one. No, nothing. There's no way. Well, is this even smaller? Oh, nanofarads. Man, this thing don't work, that's for sure. My capacitor's cooked. Okay, let's get out of here. Ooh, let's turn the exposure down just a little bit. Let's see. Better? Yeah. Apply. What about me too? There. Okay. We're really not. Oh yeah. We haven't measured this one yet. Oh. Okay. Let's put them in. Come on. What the? There's no way I broke it. For real? Or am I just not getting a measurement? Oh my gosh. I'm not getting a measurement. Oops. Okay, that's his peak. Let's say 60. The smaller this is, the smaller our no, the smaller this is, the bigger our inductance will need to be. Oh. Okay, that one's too big. That head. Yeah, that one's too big. Do the smaller one here. Alright. Yeah, we didn't get to try him. Let's try him. I want to see what he is. Let's just use what we got. Okay. Here's the pen. So that was 0.060 nanofarads. C3 equals max. It's not really max, so we'll say 65 nanofarad max. Okay, for the calculations. Okay. So we know what our capacitance is. Maximum. Yeah, I guess that's... for 2K. 65. Because it's variable, so then we'll be able to change the frequency. But what do we want to allow for? Like a swing? So should we do half of it? Which is like 45. Let's call it 0.045. Its range. Yes. Okay, we'll do that. So 0.45 e to the negative 9 times 16 e3 times 6.5. Oh shit, for real? My frequency must be small fry. My frequency is small fry. That's why. I'm gonna... Jeez, my frequency is gonna be... Oh no. Pretty sure this thing has a maximum of 20 kilohertz. So that would be... Oh man. Okay, so 20... Right here, F equals 2 pi 4. Yeah, so let's say 18. Yeah, so whoops. So 36 squared. Okay, so that's 1 mega, 1.2296. We gotta change the frequency from kilohertz to 1.296 megahertz. Okay, megahertz. L2 equals... Okay, so 0.06 e to the negative 9 times, can you see that? No. Oh yeah, you can. That's still too much. Oh, it is. I need to turn down the brightness of my calculator. I don't know if that's a possibility though, but anyways, oh yeah, wait, 0.045 e to the negative 9 times, because that's nanofarads, multiplied by, because we're doing this, pi squared, yeah, pi, what the, wait a second, squared, times 1.296 e to the 6 times 6.5. Now we get a inductance of 3.74. Oh my gosh, it's still high. 3.74 741. How interesting. Because my capacitance is... What size is my capacitance again? Nanofarads? That's tiny. If I had a bigger capacitance, I could also have a less... That's the only variable I have though, so let's mess with it. Let's mess with it. Wait a second. Oh. Right, hold on. Okay. We're gonna see. 3.741 millihenry, yeah. Forgot. Okay, millihenry. Do I have that? I do. Absolutely. I have a 2.2. 4.7, 2.2. We want to go, let's go smaller. 4.7. 2.2 is further away than 4.7. Okay, we'll do that. So we'll make him an approximately. We'll make him an exactly 4.7. I guess it's still not even exact until I measure it. If I did have an inductance, but I don't. Okay. So now. Oh, getting some farads now? What? They're not connected to anything. There's just some, there's a electric field in the air. It's moving further apart. What, really? It's a self-capacitance? No, because I put them closer together, it didn't change. $77. Wild. Okay. Oops. So we got L2 and L1 is determined by, so L1 equals 5.5 times 20.6 millihenry. 20.6 millihenry. What do we have? 220. No. Yeah, I guess so. Okay. I mean, what? That's literally it. Wait a second, though. The frequency, no. Yeah, the frequency is only... That's a... Yeah, my oscilloscope can't measure that. That's the thing. So let's change the capacitance. So let's keep for where we got 2 kilohertz and we got to 16 kilohertz. Let's keep this. L2 equals, no, that's okay. Yeah, let's rewrite this. L2 equals 1 over C pi squared 6.5 times, we're gonna go back to 16 kilohertz. Yeah, that, no, I'm forgetting what one thing. No, that's it. Okay. We're gonna make the capacitance. It's gonna be, I don't know what's the word, non-changing capacitor, just an electrolytic capacitor, but like there has to be an opposite to variable capacitor. Whatever, bro. Whatever. Okay. And we have all sorts of values of these. What was I just at? Nanofarads. So we want to increase it. So we have 220 or 2,200 microfarads. Micro e to the negative 6 times pi squared times 6.5 times 16 e to the 3 equals to the negative 1. Yeah, so 440, 443, 43, 330, 470, 470 microhenry. Wait, not, yeah, microhenry, yes. Okay, 470 microhenry, so that's what we'll use. We'll have a, oh yeah, C3 equals 2200 microfarads. Did I say farads for the inductor? I meant Henry. Yeah, it's small voltage, so should be able to handle it. I forgot what it's rated for. I think it's like 10 volts, which isn't very high, but granted, that should be fine. 470 microhenry. Yeah, okay, so now we got, so C1 L1 equals 470 this times 5.5. 2.43 millihenry. How did I get that wrong before? L2. Oh, because I label them both. No. Oh, never mind. Okay. Never mind. Okay, for the radio frequency choke, I'm probably going to have to make my own solenoid. And then I'm going to have to determine its inductance. Oh, man. I'm going to have to pull out the physics textbook, or physics notebook with my notes in it, but... That's a Colpitts oscillator. Okay, so we have these values. Let's hook it up. Let's do it. Not this one. Where is he? Here he is. And then we'll get measuring the frequency too, to ensure that it was our... Oh man, I'll deal with that in a moment. Deal with the battery in a moment. Okay. Yeah, we're just gonna hook it up and see if it works. So I need I said 470. Where's that at? I need the pliers, the pinchers. I need the pinchers. Fuck it. Brother. Oh man. Oh, there they are. Okay. So much easier. This is L2. Okay, so L2. So we'll get him to ground there. 470. L1 is 2.44, 2.2. Oh yeah, you can't see that. Or this. There. From above. Okay, so that's 2, that's 1 right here. Both connected to ground. Come on. Alright, there it is. Alright, we need the 2,200 microfarad capacitor. That's coming up right here. Whoa, only have 1 in there? Yeah, it's rated for 10 volts. Do I have, wait. No, that is it, 10 volts. Ah, okay. I literally only have 1. I'm gonna make sure it's discharged. Yeah, it's good. Okay, and this is gonna go across them, starting from R or L1, and then the bottom of it L2, just like that. Oh, whoops! I'll show you guys. It was like that. Oh man, it could almost be further away though. I don't like the way it's sitting in there. It's going to be further away. Wait, I got this the wrong way though. There, that's way better, and we'll change that up. There we go, just like that. Come on, buddy. There, okay. That's the input, and that's coming from the base of the transistor, so we'll connect in now. Let's see, to the base, is that enough? Not really. Oh man, I'm kind of running out of these shits. They just get lost, I don't even know. This should do. Wait, that's grounded. This right here is coming from the base. After into the capacitor. So this is the input. Ooh, okay. Actually, I have a shorter distance than I thought. That was actually set up nicely. So right here. Ah, shit. Where is it? Ah, there it is. There we go. I don't want all that curve in there. It's too much curve. It itself is going to acquire some mutual inductance. I don't want all that shit. Come on now. Okay, so I think that's looking good so far for the Hartley oscillator. Okay. Now, what do we want to add to here? Yeah, we want to connect that to ground. So we're going to need just a real small guy. How small? Alright, I don't know. I'm being picky about it. Let's do this. Come on now. Oh my gosh. take him out for now. I got such a small space. There. Not hitting. Brother. Oh my gosh, I'm having such a difficult time. Okay. Are you kidding me? I never have this much difficulty trying to get this shit in. Let's go. Okay. No, let go. Brother, what the fuck is up with that side? Maybe this time. There, okay, yes, okay. Positive, negative, that's ground too. No, I fucked that up. At least I caught it now though, that's good. At least I caught it now. Okay, actually we're gonna need this orange guy and he's gonna be our ground. So something like that. Okay. He's gonna connect to here. There, like that. And he's the feedback loop. There, that's what I needed. He's the feedback loop. Okay. Can you see that? Yeah. It's a little dark in it. What the? Yeah, I guess it was too dark, huh? Man, it's not one to go in. What the? There. Okay. Whew, that was tough. Let's do this now. Boom. Right in there, like swimwear. And our output is at the transistor. There. That's our output. I gotta double check that everything's grounded. We're gonna need our 9-volt battery, our supply. And get rid of this. That's right. Okay, I'm thinking CE. We need CE. We also need RE. It's missing from the circuit. I don't know what happened to it. I don't know why I was drawing a blank, but I remember now it was 10 ohms. So where's my 10 ohms? Is this it? Right? Yeah, that's 150. That's 68. Oh, I'm also missing my 6. Oh no, that's there. Yeah, just the 10 ohms. What the heck? Where'd it go? No, that's not it. This must be it. Let's see. Definitely not it. Oh. This one. This must be it. That's it. Oh, you can't see. Alright, there it is. So and that's to ground. You see that? Yeah, you can see that. I guess that's not connected, so that's fine. Here, I'll show you a little bit closer. So this portion is just our LC tank circuit right here in parallel, and then this here is our entire common emitter amplifier. Common emitter amplifier. It's all just right here. Okay, and this is our LC tank circuit here. That's going to establish the frequency that we operate, and then through the feedback loop is going to switch on and off this transistor. Switch on and off. Well, not. I guess that's the wrong terminology, but it's going to amplify the signal so that it just continues to go about the circuit. It amplifies it. Yes. This is going to the conservation of energy still applies because this will be drawing energy from the battery. I guess draining it every pump, every oscillation, or like, I don't know. I guess it's an interesting question. Granted, it gets through or it gets started by, I guess, well, I don't want to rant about stuff that I don't fully understand, but here's the circuit thus far. Okay. No, we're not going to use the variable capacitor, so there's that. Now we have him connected to ground, correct? Is that even? Yes, it is. That's ground. Okay, we only have one opening. We got that. We're going to take the output there. I believe that's it. What's going on with him? That's the output. Okay, that's the output. So there's that. He's connected here. What is he's not connected to anything. Nope, there's that. He's connected. Yeah, that's a part of that. Goes to to him, to the 68. That goes to the base. Yeah, right. To set up the voltage divider. To set up the voltage, indeed. And then that's the signal amplified. And that's our output. Okay. Wow, how interesting. I hope this works. That would be incredible if it did. So So now we would need to hook it up. Okay. That's it. That's literally everything. Let's get grounded. And then he's connected. Yeah, and then those are grounded there. He's connected across there. Coming back to him. Oh yeah, that's the one thing I wanted to add was CE across R4 to short it. But what's a good how is this going to affect my gain? Yeah, the lower the frequency, no. Yeah, very small reactance. Okay, so higher frequencies get through easier. I say whatever. Let's try it. I say whatever. Okay, and then that's going to be our input. Right at the 68, and right to our voltage divider. 68 ohms. Straight to the collector of our transistor. Okay, let's set up our probe. Our oscilloscope probes. Right to the output. Let's not measure him. Measure him. Yeah, just like that. Ground him. Oh, weird. Input. Okay, that should, I mean, what, you can see that? That should be good. Okay, so far nothing. And what are we connected to? Channel 2. Wait a second, 18 kilohertz. Ooh. Is that a reading? 18 kilohertz? It's just not a high enough gain. I changed it. That's why, right? Okay. Oh, it's still 18 though. Oh shit. Still 18 kilohertz. It's probably not a high enough gain. In all honesty. Man, why is it getting readings? Let's see. Huh. Let's see, That's kind of low. No, let's see, yeah, we did lose some juice in the battery. Oh, I shouldn't have turned that off. That's not good. I guess that's what happens, right? That fuck up all my calculations like that. He's not any better. There's a different battery. I'd have to recalculate it. Back to the drawing board. So what is it that I need to fully recalculate? Well, this would go back to the common emitter amplifier then. I would go back to that. I guess we could do that then. Shit. Alright. That didn't work. Yeah, we have to establish a common emitter amplifier with like, let's do like a gain of 100. Yeah, that's probably gonna be a lot better. Oh man, I don't know where to put him right now. I need to build something. Okay. So let's let's do a new page. Do a common emitter amplifier. I got it. See, I had some stuff going here, as you can see. Okay. Just trying to think where I want to draw it. Ah, man. I forgot my capacitor, my coupling capacitor. Oh well, it's okay. Wait, actually though. That's interesting. Okay. Okay, and that's right, we got this. Oh yeah, I'm probably not gonna do him though. Wait, pause. Pause on that. I'm probably not gonna put that capacitor in there. Okay. Like that. Yeah, grounded. And then he's attached to here. Yeah, I like it like that. Cool. Oh yeah, wait, 8.07. Is that right? Let me look again. Oh. Okay, that's what we're gonna use. 8.880. I got too much stuff going on. Holy smokes. Okay, 8.880, yeah. 880, that's what it was. Yes, 8.880 volts. Okay. How crazy. RC, R1, R2, RE. Yep. Okay. L1, L2, C3. Oh yeah, C. Is that C1? I forgot. Yeah, C1, C2. Okay, sure, but we're just gonna look at. Oh, I drew everything. I didn't mean to do that. Okay, let's isolate the portion that we want to study. Maybe we will do the small signal analysis and analyze the way this capacitor here affects the signal, the small signal, and a small signal analysis. So, but right now we're just gonna set up the DC operating point. And again, that's our 8.880 volts. Okay, just like that. Can you see all that? Yes. Okay, again, we'll do this. I mean, I don't know. It's just an aesthetic thing. I really just fucked that up. RC, RE, R1, R2. Okay, we're going to, so, ground. Okay, desired. I'll put that on. Beta approximately, yeah, shit, I was gonna write equal to again. Approximately, let's say 125. Let's shoot for that. 125. So AV equals 125. And again, we know, oh yeah, AV over, yeah, we'll figure that out later, but right now we just need this. So, okay, we know that. We want to set that up. So AV 125, and what do we want for IC? So the current here, IC, that's going to be be determined by the current here, IB. And so IC, jeez, man, I keep getting caught under the table. Okay. Weird. What's stream chat? Alternate Academy. Academic Ian. I don't know. It's odd. Whatever you said. Like what? Seems a little sus to not remove the space, then put in parentheses remove the space. That doesn't even make why that's sus, dude. Super sus. Okay. All right. So desired beta equals 125. So now we must determine what do we want. Desired IC equals that's our signal output. I guess just within the range of our oscilloscope. Wait. So really I want, wait a second. So let's define AV equals V V out over V B, or VC over VB. VC over VB. Okay. So here I'll show you that. So this VC, yes, and VB to ground. To ground. So if that's to ground, VC equals VCE plus VE. And so now we have to, can you read that fine? Is it like a real fine print? Nah, you can read it pretty well, actually. That's not bad at all. That's not bad at all. Okay. Yes. I'm just going back in the stream right now. I'm looking at everything. I just kind of want to see how it all looked. It'll start off kind of slow. I wonder how my commentary's been. I wonder if it's been dog shit. Word. Okay, that's kind of fire. And now I'm just back to me looking. All right. So VC over VB, and then we know that VC equals the voltage from collector to emitter plus the emitter voltage right here. So collector emitter. Okay, collector emitter voltage. So just like that. Yeah, so now we just labeled some stuff. Let's figure this out. I'm trying to think. VCE. This is what you want to be half of yours. So we want VCE to be, see that? Yeah. Which is 8.880 divided by 2. That's what we want. So 4.44. I guess, yeah. Could have done quick math. Oh well. So VCE, so VC equals 4.44 plus nah, that can't be what we're... Yeah, that's not the right output. So the output would come from the small signal analysis. It definitely would. Okay, so what do I need? So I need the current. So we're just gonna solve for the current first, and then we'll worry about that here in a moment. Beta equals 125. Yeah, we'll worry about that later. 125. Well, that's what it would be. So our L1 was... Let's actually add the load resistance too. Yeah, that's it. So... yeah, that's good. RL. That's our load resistance. Okay, and so that's going to be, what was L1 again? L1 was the bigger, so it was the 2.2 millihenry. 2.2 millihenry, and that had 6.3 ohms. .3 ohms. Okay. Yeah, whatever. VCC. So, okay. But just for the current, so 6.3 times we're going to do 75 milliamps. So that's right, and now we're gonna want to solve for that. So 75 milliamps, 75 e to the negative 3 divided by 125 equals IB equals okay. The 0.6 milliamps or 600 microamps. That works. Okay, 600 microamps. That indeed, 600 e to the negative 6 times 10. So we want this to be 0.0066 milliamps, and 11 times 600 e to the negative 6.6, right, milliamps. 6 milliamps, 6.6 milliamps. And in order to acquire this, we want VB to equal desired. Oh, I didn't put that down here, shit. Equals 1.6 volts. Okay, that's what we want at 6 milliamps, 1.6, right? According to Ohm's law, I guess I don't know if I need to write all this out. 1.6 volts divided by 6 milliamps equals our resistance, R2. So I had it, divided by 6 e to the negative 3, 266, and that's really? That's the thing though, what kind of let's just try it. Okay, so R2 equals 266. Well then, what's an actual value that we have? 220, 266, 330. I have a lot of 330s. So, what is this going to change? 1.6. That's all it would change. And so, okay, so let's say we want R2 equal to 330 ohms. So 330, we got 1.6 divided by 330 is a 4.84. Okay, so we're gonna make IB equal to 4.85 milliamps, and then 125 times 4.85 milliamps e to the negative 3 is 606 milliamps. No, it's way too much. See, what the wait a second, no. Okay, so 1.6 divided by let's say like 2,000. So times 125. 100 milliamps. I don't know, it's kind of a lot. Yeah, see, I've been recording longer than I've been streaming, so it must have went out. Must have cut out. Oh, I guess it's not that much of a delay. What happened? Oh man, but I've been going on an hour 45 on Twitch, but only 105 on 30 plus platforms at once. Whoa. Okay. 330. No. Let's go. All right, let's redo the 75 milliamps. I don't know what happened there. E to the negative 3. Yes, 75 milliamps. Divided by 125. And I put IB equals 600.6 milliamps. Did I mess that up? 0.75 divided by 0.6. 125. Okay, maybe I messed that up. So 1.6 divided by 0.6 e to the negative 3. Ah, okay. I did mess it up. So actually we want R2 to be 2,666. I don't like that. approximately equal to 2700. I'm gonna round up there, ohms. I can achieve 2200 plus. I don't know what I actually have. Oh man. I don't actually know what I have. So let's see. Oh man, look at that. Instantly found the 22K. That's beautiful. Wait, what did I need again? What was it? 27. Okay, so. Oh. Okay, so let's say, what if we had oh, that's 22K. No, okay, I fucked that up. That's all I wanted. Okay, there's a 470. I'm pretty sure I'm gonna need that. I just need a 2200. 150, 15. No. I don't have any up here. Man, I need to organize my shit. Ooh, okay. Found a 1.5K, 100K, 2K. Oh. That's fine. So we'll do 2,470. Let's just mess with that and see what that gets us. Okay. So let's say equal to 2,470. Yes, ohms. Whoops, that was a bad omega. Okay, 1.6 divided by 2,470. So, okay, I base equals, now this is for sure, well, not necessarily for sure, but a lot more accurate. 6.4, so 0.648 milliamps. Okay, and we're going to amplify that to 75. So IC is still 75 milliamps with a gain factor of 125. Okay, so now we know R2. So we know R2. Wait, IB. That's not IB. Wait, that's not IB. 75. Fudge. Divided by 125 is 0.6. IB is still 0.6 milliamps. So that's not IB. That's I2. That's I2. I2. Okay, no, I'm making a mistake here. Okay, so IC, okay, I2, so 1.6, yeah, divided by this number, 2,470, so that is accurate. And that's IB is still, we'll put that here. 0.6 milliamps. That's still IB. Okay, so now we got that. 2,470 ohms. Okay, we have that. Literally got it here. We're gonna put a 2,000 ohm resistor and a 470 ohm resistor in series. Okay, so now we know this. If that's going to be a 1.6 voltage, we need 1.6, but how would I determine? By the ratio. So let's figure out, okay, let's solve for R1 through the voltage divider equation. So that's gonna look like, where do I got room? Right here. It's gonna look like this. V1 equals, yeah, that's what I want to know, yes, equals VCC. Okay, and then yeah, R1 over R2 plus R1, and we want this to be whatever 8.88 minus 1.6, because that was our base voltage. So we want this to be 7.28. So 7.28 divided by 8.88 equals R1 over, okay, so we're gonna go, what is R2? 2,470, 2.470 kilo ohms plus R1, equals R1, so 7.28 divided by 8.88 times 2,470, 24.95 equals R1 minus 1 minus this 0.1801. I could have made that a 2. R1. Yes, and then that divided by, oh wait, yeah, R1 equals 11,238 ohms. Okay, let's see what I have. 5 points, no, we don't want that. Oh yeah, wait, I found a 1 point. Oh my goodness, okay, I have a 10 and a wait, no, that's not what I want. Okay, I got a 10K and a 1.5K. Okay, so this. So now, okay, so for a third time, now we can really solve for IB, because 7.28, yeah, divided by 11.5, E3, sure. So, okay, I1 equals, yeah, no, that's accurate, 0.633 milliamps. That means I2 equals 1.6 divided by 2,470. No, 1.6 divided by 2,470. Brother, what the what? Wait, what? The voltage isn't, that's why, okay. So, not this, that's not what I want. No, I don't know that. That's not what I want either. So, now V1 equals, okay, now I'm just gonna do it. So now V1 equals, 8.88 times 11.5 E3 divided by 11.5 E3 times 2,470. This V1 equals, whoa, wait, what? What did I, oh, I did a multiplication, shit. It's supposed to be an addition, okay. 7 point, okay. 0.0, ah, shit, 3, I'm all sorts of messed up now. V1 equals 7.310 volts. 8.88 minus this. V2 equals 1.57 volts. There, so now 7.3 divided by 11.5 kilo ohms. So I1 equals 0.636 milliamps. I2 equals 1.57 divided by 2,470. And it's the same number. Okay, maybe not the currents, but no, okay, let's not consider the currents yet, I guess. I have to do more than just that. I beta 0.6 remains the same. I beta remains the same. No, it doesn't, but we'll solve for it. But this is just what I need. $1.57. Okay, with those numbers, yes. Okay. Oh man, I'm hungry. Like really hungry. But I do kind of want to keep streaming. I don't want to stop, but I am hungry. What would you do for a Klondike bar? What would you do for a Klondike bar? Oh yeah, that sounds nice. That looks nice too. What would you do for a Klondike bar? Oh yeah, that sounds nice. That looks nice too. What would you do for a Klondike bar? Oh no, it's echoing. Man, I do want to make it work though. That is absolutely true. I want to make it work. Um, I want to see it work. I want to record it with the oscilloscope and see the frequency that we've established. So to get this amplifier working, what else? VC, no, whatever. RC. In order to know AV, yeah, we're gonna have to do the small signal analysis. So, but this is what we want to shoot for. We want to shoot for the gain of 125. Now, in regards to IC equals beta. Yeah, we know IC is 75 milliamps. So what is this going to tell us? Right, so that would, okay, so the voltage divider, what, it just gets us in the ballpark? Just gets us in the ballpark. Sure. Oh no, we could solve for IB. No, we couldn't. Weird. Shit, I've kind of lost where I was going with this. Let's see. Oh, that's right. I guess we could okay, so we also want the emitter voltage VE to equal, oh wait, can you see that? Yes. VE to equal approximately, which we're just going to calculate it as, we'll say 1.5 volts, 1.5 volts. So if we have VCE, so VE is going to equal, yes, so VE will equal 8.88 VE. Yeah, that's it, plus. No, divided by 2. There, plus 1.5 volts. Okay, so. Okay, that gives us 5.94 equals 5.94 volts. Shit. Volts. Okay. I gotta rewrite that. 5.94 volts. That's VE. Write it here again too. Equals 5.94 volts. Okay, so we know that VE, that's across there. If that's 1.5 volts, well, no, because I wanted to know that for the purpose of what? What purpose? Oh, I guess to knowing what's across RC, and then we know our. Oh, okay. So. Yeah, so RC equals 5.94 volts divided by 75 milliamps. That's what it is. 5.94 divided by 75. Come on. E to the negative 3. Okay, so that equals 79.2, 75 e to the negative 3. 79.2 ohms, and we have, what do we have? We have 79.268. Yeah. So RC, if we have 68 ohms, we have 68 ohms, 75 e to the negative 3 times 68, 5.1. So we really want VE to equal 5.1, and if that's the case, 5.1 minus, or 8.88 divided by 2 minus 5.1 equals. Whoa. Oh, that's not. Oh. Wait a second. Oh, shit. No. 8.88 minus 5.1. That's what I want. No. Okay. Oh, that's wrong. VE. So VE. So VE equals 3.78 volts in real life. 3.78 divided by 68 equals what? How is it not 75? That's what I maintained throughout that calculation, that manipulation. How is it not 75 milliamps? It's 55. What went wrong? 8.88, yeah, divided by 2 plus 5.94. No, that's obviously wrong. What did I do wrong? that's not it. 1 point, oh, that's why. 8.88 divided by 2 plus 1.5. 5.94, okay, that's why. Divided by 75 e negative 3. 79.2, right. 68. Still though, I should have maintained that because I changed the voltage, correct? Voltage, because I said, yeah, 75, 68. So 68 times 0.075, 5.1. Wait, what? Yeah, so 5.1. 5.1 divided by 68. Yes, okay, 5.1 divided by 68. RC, VC. So RC, VC equals 5.1. 8.88 minus 5.1. 3.78. So VE equals 3.78. VCE equals, oh shit, 68. I need more than that. So 68. Let's go. Yeah, 100. So 100. $75 milliamps times 100. Wait. Oh fuck. No, I need to go smaller. Okay. So